In mathematics, if is a subset of, then the inclusion map is the function that sends each element of 2, treated as an element if. A hooked arrow is sometimes used in place of the function arrow above to denote an inclusion map. This and other analogous injective functions from substructures are sometimes called natural injections. Given any morphism f between objects x and y, if there is an inclusion map into the domain, then one can form the restriction phi of f. In many instances, one can also construct a canonical inclusion into the codomain Ry known as the range of f. Applications of inclusion maps. Inclusion maps tend to be homomorphisms of algebraic structures, thus, such inclusion maps are embeddings. More precisely, given a substructure closed under some operations, the inclusion map will be an embedding for tautological reasons. For example, for a binary operation, to require that is simply to say that is consistently computed in the substructure and the large structure. The case of a unary operation is similar, but one should also look at nullary operations, which pick out a constant element. Here the point is that closure means such constants must already be given in the substructure. Inclusion maps are seen in algebraic topology where if A is a strong deformation retract of X, the inclusion map yields an isomorphism between all homotopy groups. Inclusion maps in geometry come in different kinds. For example, embeddings of submanifolds. Contravariant objects such as differential forms restrict to submanifolds, giving a mapping in the other direction. Another example, more sophisticated, is that of affine schemes, for which the inclusions spec and spec may be different morphisms, where R is a commutative ring and I an ideal.